So when we talk about equilibrium, right? We're talking about equilibrium of other reaction classes, other than acids and bases, you know. So we still have other types of reactions. So we've seen these precipitation reactions. Um, but why do we need to know this equilibrium, right? Well, part of the reason we just kind of need to ask ourselves is we know that we could take a solid and dissolve it into ions, or we could take these ions and turn them into a solid. But initially, it comes down to is how do you control dissolution, right? How do you control dissolution? How do you control precipitation, right? And the answer to that is calculations. How do we control it? Well, we calculate KSP. We calculate these solubility products, right? We calculate molar solubility of the molar solubility of ions. And this is how we control this dissolution or this precipitation, is by understanding how this works at equilibrium, right? At equilibrium, am I going to get a precipitate? Am I going to uh, get some ions? Is this solid going to dissolve, right? And we can easily apply this to a couple of scenarios that let's take when you have an upset stomach. If you have an upset stomach, when I have an upset stomach, I don't know about yourself, but um, we take some antacids, some called Tums, right? I have some Tums if I ever have feel a little heartburn or get a little upset stomach. I take some Tums, but what's in Tums is carbonate, right? So if I take a Tums tablet is just essentially some calcium carbonate. So I take this solid and I'm hoping to dissolve this solid once it gets down into my stomach, right? And it breaks down into these calcium ions that the calcium can be used as just electrolytes, but these are aqueous. And this here, right? This is what's going to soothe my stomach. That's what's going to soothe my stomach. So I need to know. It has somebody has to determine this when they're making Tums. Somebody has to determine the concentration at which this is going to become aqueous. At what point is this going to dissolve? If I take it, I don't want it just to remain a solid in my stomach. I want this to dissolve in my stomach. So somebody has to know the concentration at which point this is going to dissolve into ions. Um, that see here. We could take it a bit further. That just the opposite effect of that is that uh, no, not calcium. We're going to use calcium though. Is that in wastewater? There's a bunch of phosphate in wastewater. The wastewater comes from all the cleaning materials that we use when you're doing your laundry, whatnot. All that phosphate is sent down to the water treatment plant, right? Because they have to clean our water before they send it back out to us. So phosphate, um, they have to be able to precipitate that phosphate out, right? So one way to precipitate that phosphate out is that um, in wastewater, there's also some calcium ions. right? It's just a mineral. It's in calcium. Let's see. And I better write the whole thing over here. So this is what precipitates out of this reaction. We got phosphate side, and this is solid.
Negretti,
Yes.
if CO3 is two negative, shouldn't there only be one on the left? Or is it just one negative?
Oh, CO3. So if phosphate is in the water, um, there should only be one. Oh, wait, what am I doing? Yep, calcium is 2 minus. What am I doing? This is 2 minus. There should only be. There we go. Does that look better? Sorry about that. Um, so how do we get phosphate to precipitate out? Right? How do we get phosphate to precipitate out? Well, there's one way to do that, is that we can add into the solution or into wastewater. So if this is our wastewater here, if this is our wastewater, is that if we add some calcium hydroxide into this, well, we can also bring in Le Chatelier's principle, is that here, if I increase this concentration, well, that means that this concentration is also going to increase. And we're going to decrease the amount of phosphate because this will shift to the left. So this is why we do all these calculations, is that we want to get phosphate out of the water. Well, how do we do that? Based on equilibrium, based on precipitation? Well, let's add in some calcium hydroxide, and we're going to push that reaction to the left, and we're going to get all this phosphate out of the water. And we'll just have it precipitate out as a solid, and then we can filter that water out to remove all that phosphate out of there, right? Um, this also happens to be, we can look at it just one more way, is this also happens to be the calcium that's in your teeth, right? This is the calcium that's in your teeth. Well, if we don't learn how to control equilibrium, well, you want to make sure that you do everything. You know what? I don't want to get rid of that just yet. I should leave that arrow in here. You need to do everything that you can so that, I mean, if this is your teeth right here, is that you want to do everything you can in order for your teeth not to decay, right? That if we look at it this way, that this is going to be tooth decay, right? You right. We have to be able to make sure that everything that we're drinking and eating, and a lot goes into so that we're not promoting tooth decay. Is that I don't want the calcium in my teeth to turn into calcium ions, phosphate ions, right? So all of this here, this specific chapter is just dealing with how to control this dissolution. How do we control the dissolution so that we keep the solid? How do we control the dissolution so that we dissolve the solid? And it's all done by a matter of calculating KSP, calculating molar solubility, the pH at which we need it, the concentrations at which we need it to either shift this reaction to promote the solid or shift the reaction to promote these aqueous ions. So I just wanted to take just a couple minutes into the chapter or this morning, just to kind of reflect on why we're doing these kinds of calculations anyway. So we didn't get to precipitation of halides. Should we do a little more on the common ion effect? Yeah, let's go. It'll just stay with the book here. So we're talking about precipitation of halides. So if we propose some kind of problem, and let's take some silver nitrate. If we take some silver nitrate and add it uh, to a solution of 0.50 molar chloride, and we're going to also add it to 0.050 molar bromide, is that silver bromide and silver chloride will both precipitate, but which one will precipitate first? Right? We know that silver chloride will precipitate. We know that silver bromide will precipitate. But if chloride, bromide are in the same solution and we just simply add some silver nitrate to it, well, which one of them is going to precipitate first? Well, it comes down to the concentration, the one with the smaller concentration, because essentially the one with the smaller concentration is going to have the smaller KSP. And we know that the smaller the KSP, uh, the more that it's going to remain as a solid. It's going to push that reaction as a solid because of such a small KSP. So essentially it comes down to knowing which one has a smaller concentration. So there's two reactions that we do need to look at because we have two different ions here that can both potentially make a solid, right? So we can look at silver chloride, solid, and this is going to be made from some silver ions plus some chloride ions. And then we have some silver bromide as a solid, and that's going to be made from silver ions and some bromide ions. Let's see, the KSP here. Let's see what the KSP is here. Let me open up the book. KB. There it is. So we have silver chloride. So silver chloride is 1.6 times 10 to the minus 10. 1.6 times 10 to the minus 10. And silver bromide is 5.0 times 10 to the minus 13. 5.0 times 10 to the minus 13. Well, here we do know some concentrations here, right? Is that looking at the very first reaction here, is that the KSP is equal to concentration of silver ions times the concentration of chloride ions. And we do have that concentration. So we can figure out what the concentration of silver is here by simply plugging those values in. So we've got 1.6 times 10 to the minus 10 is equal to the concentration, the molar solubility. I keep saying concentration. I'll say the molar solubility of silver times 0.050, right? So that the molar solubility here is equal to 3.2 times 10 to the minus 9. So we figured out the molar solubility of the silver ions for silver chloride. Well, now we can do the same thing. Let's see, so our KSP is equal to molar solubility of silver, but this time the molar solubility of bromine, and that's going to equal 5.0 times 10 to the minus 13 is equal to solubility of silver times 0.050. And here, our value is 1.0 times 10 to the minus 11. So between these two concentrations here, the smaller concentration, the smaller molar solubility is going to precipitate out first. So silver bromide will precipitate first. So, this is just kind of a continuation of what we always talk about, this silver, I'm sorry, this common ion effect, right? That we bring in these other ions to shift the reaction one way or another, is that we have what we call common ion, the common ion effect here. So say we had some acetic acid, nope, H2O, what am I doing? H2O, and we're going to get some H3O, plus we're going to get this conjugate base. So, excuse me, the common ion effect is is when we're going to add a common ion. If we introduce a common ion into this reaction, well, how can we shift this reaction, right? So a common ion here is let's take a look at, right? So this is sodium acetate. So we have acetic acid that makes acetate. Well, if I introduce sodium acetate, well, that's a common ion, right? Na plus CH3COO. Is that here, this is going to give me Na plus some sodium plus this common ion. So here, right? common ion. So if I introduce some sodium acetate into this reaction, well, what I'm doing is I'm increasing this here. I'm increasing the amount of acetate that I have, right? And if I increase this concentration, well, we're going to shift this reaction to the left. If I'm going to increase that amount, I'm going to increase this amount by adding that particular ion into the solution, right? So we use these common ions in order to push the reaction to the left or push the reaction to the right. So let's look at a problem that actually takes this into account here. Is this common ion effect? So let's calculate molar solubility of aluminum hydroxide in a 0.015 molar solution of aluminum nitrate. So calculate the molar solubility of, this doesn't, looks like an L here, let me fix that. So calculate the molar solubility of aluminum hydroxide in a solution of aluminum nitrate, right? This does seem a little bit confusing. Let me kind of draw an image of what's going on here. So here in this beaker, I have a solution, a 0.015 solution of aluminum nitrate. Aluminum nitrate is soluble. So this is what we kind of have floating around in the solution. Right. So what we mean by calculate the molar solubility and the use of this common ion effect is that here I have this little chunk of aluminum hydroxide. So I have this solid piece of aluminum hydroxide. Well, what's the molar solubility of this? How much of this is going to dissolve? Right? That's essentially what we're asking is how much of this, the calculated molar solubility, how much of this is going to dissolve in a solution of 0.015 molar aluminum nitrate. Well, let's see if we can find the KSP for this real quick. Aluminum. There it is. 2 times 10 to the minus 32. So our KSP of aluminum hydroxide is equal to 2 times 10 to the minus 32. All right, and let's write our reaction for how this is going to dissolve. So we're talking about aluminum hydroxide, solid, dissolving into aluminum plus some hydroxide, and these are both aqueous. All right, well, let's come out with some ice table here. I'm not going to worry about our solid. So when we're looking at this, we do have a 0.015 solution of aluminum, right? We already have that concentration here. So the concentration is already 0.015 molar. Even though we're talking about the molarity of aluminum nitrate, that's the initial concentration of my aluminum is 0.015. I don't have any hydroxide in that beaker, in that solution yet. So here, by adding, we're going to add. By adding more aluminum, The change is I'm going to be adding more aluminum. I'm going to increase that value, right? Is that we're going to increase this concentration. So then we get 0.015 plus X, and then we get plus X, and I'm looking at my KSP value, and my KSP is a lot less than 1. So I'm going to make an assumption here, and I'm not going to put 0.05 plus X, I'm just going to use the 0.05 here. So our KSP is going to equal, oh, and this should be, let me make one correction here. This should be plus 3x because of, don't want to forget that. So I'm going to make an assumption because our KSP is a lot less than 1. Write it off to the side here. We're going to make an assumption here. So we're going to say 0.015 times 3x to the third. Well, we know what the KSP is already. So our KSP is equal to 2 times 10 to the minus 32 is equal to 0.015 times 3x to the third. So we go divide this by 0.015. Let's do baby steps here. Let's see, step by step. Uh, 2 times 10 to the minus 32 divided by 0.05 is equal to 1.33 times 10 to the minus 30 is equal to 3x to the third. Let's go ahead and divide that by 3. 1.33 times 10 to the negative 30 divided by 3, 4.43. And please double check my calculations as I'm going along here. 10 to the minus 31. And this is equal to x to the third. So this is how you're going to do it. If you have if you can do the cube root of this, there's 2 ways to put it into your calculator. So you're going to put this into your calculator. 3 times 10 to the minus 31, and that'll give you some answer. And the other way to do this is if you put in parentheses here, you're going to put 4.43 times 10 to the minus 31. And then I also put these in parentheses, even though my calculator is pretty fancy, is I put these in parentheses as well, to the 1/3. And that can also give you a cube root if you don't have the cube root button there. So let's see what we have here. 4.43 to negative 31. Oh, nope. Huge mistake, Alex. Let me erase some of these values here. Oh, huge mistake. All right, let's back this up. Let's back this calculation up a bit. See these parentheses here? I removed them. I should have put them this way. So we're not going to divide it by 3. is that we actually need to divide that by 27, right? 3 times 3 times 3 is 27. So 27 will get rid of that cubed 3 there, uh, because we're cubing that whole thing. So let's go ahead and just recalculate this one more time. So 1.33 times 10 to the minus 30 divided by 27, and we get 4.32. 32. Then take the cube root of that. That looks better. And both answers should be the same here. 3 point, I'll put like 3.7, I guess. 3.7 times 10 to the minus 11. 3.7 times 10 to the minus. Either way that you wanna do that. But this is equal to x. So now we can get the concentration of both the aluminum and the hydroxide. So we're calculating the molar solubility. So we have 3x, so we have 0.015 plus 3.7 times 10 to the minus 11. Um, 0.015, and then what do we have? Our concentration of peroxide, 3 times 3.7 times 10 to the negative 11. That's a 10. Right? Could we figure out pH from this? Yes, we could figure out pH from this. Absolutely. That we have that concentration available to us. All right, so I think that finishes out just that particular section when we're talking about dissolution and we're talking about precipitation. Is that we can now get to the next part of this. So the next part of this chapter, they're talking about Lewis acids and bases. So Lewis acids and bases. So um, we have a term here that we call coordinate covalent bond. So we know what a covalent bond is. Covalent bond is metal bonded to a non-metal bonded to a non-metal. We understand that as a covalent bond. But here we have what we call a coordinate covalent bond. So what a coordinate covalent bond is, this occurs when um, when one element provides both bonding electrons, right? Normally when we're talking about covalent bonding is that we have one element sharing its electron, right? Both elements are going to share some electrons to make that bond. Well, coordinate covalent bonding happens when both of the bonding electrons come from one element, right? the simplest, the easiest example we have of this is probably water, right? Water. So if we do this, let me draw out this structure here. So we got water. I'll put hydrogen on this side, hydrogen on this side, and if I bring in a hydrogen proton, the hydrogen proton doesn't have any electrons on it. H plus has no electrons, right? Uh, Again, H plus has no electrons. If we're talking about hydrogen, hydrogen has one proton, one electron, but H plus means that we've lost that electron, and now we just have simply just one proton. So what do we get from this, right? We get, let's put it over here, right? Where this electron here, I'm sorry, this element, oxygen provided both of the bonding electrons in order to make that bond. So this is what we consider a coordinate covalent bond. And now to kind of distinguish Lewis acids from Lewis bases, right? We know that because we have some understanding of coordinate, one element providing both bonding electrons, we know the general rule for um, Bronsted-Lewis acids bases, right? If we donate a proton, it's an acid. If we accept that proton, it's a base. Well, now we're looking at coordinate, right? We're looking at coordinate covalent bonds. We're looking at which element is donating the electrons, right? So um, a Lewis acid will accept electrons. A Lewis acid will accept electrons, and a Lewis base will donate electrons. So Lewis acid is going to accept a pair of electrons, and a Lewis base will donate a pair of electrons. So let's take about zinc. So we could say zinc 2 plus, right? Zinc 2 plus, and then let's add 4 hydroxides to that. So 4 hydro. Let me put in my electrons here, right? So from this, well, Lewis acid, Lewis base, right? We already know that hydroxide's a base, but look at all these electrons here. Is that this is my Lewis base because it's going to donate a pair of, and I should say bonding electrons up here. Bonding, bonding. And because the positive charge on the zinc, this is going to be my Lewis acid. So Lewis base, Lewis acid. And what do we get from this reaction? Well, we're going to get zinc, and it's going to take one bonding pair of electrons. So it's taken one pair of bonding electrons from each one of those. Anybody want to guess the charge here? There is a charge on here. If we look at, right, look at the charges here. I have 4 hydroxides. Any wild guesses on the charge? Just a number. Take a guess. – one zinc that's positive 2 charges, and I have 4 hydroxides that are negative 2. So what's my overall charge for this?
2 negative.
2 negative. There we go. Thank you, Brenda. So it is 2 negative here. All right. So this here, uh, the combination of this Lewis acid and Lewis base, this is what we consider an acid base adduct, right? An acid base adduct. And there's another term for it as well, is that we're also going to consider this to be what we call a complex ion. This is a complex ion, right? It's not like phosphate, sulfate. I mean, this is a transition metal here surrounded by 4 hydroxides, making this with a charge. So this is considered a complex ion as well, right? Other than just an acid-base adduct. Let's take a look about this here. How about we do about some silver plus 2 ammonium. Ammonia is not ammonium. And what are we going to get from this? Well, let's see. We have Ag plus we have 2 of these. Right? Well, here it is. Here is a bonding pair of electrons that we can donate. So ammonia can donate. So this is going to be my Lewis base because it's going to donate that pair, making this my Lewis acid. All right, so let's see what kind of acid-base adduct we're going to get from this here. So we'll put the central atom as silver. There's no charge on the ammonia. So no charge on the ammonia, but I do have a charge on the silver, meaning that the overall charge here is just going to be 1 plus here. Right, so we have another what we call complex ion, but this is also another acid base adduct. Right. Let's see. One more. Oh, someone at the door? 1 second. 1 sec. Let me get the door. All right. Sorry about that. Let's take a look. So these acid base adducts. These acid base adducts can also be used. They can also be used to promote the bonding of another base. Right? We can use them to promote the bonding of another base. Is that we can take this adduct of silver and ammonia. And let's introduce another base here. How about we put in some cyanide? We'll put in 2 cyanides, and I should put the There we go. So we know that those electrons are going. Right? And what would again, it's going to displace the ammonia. So this base would displace the ammonia, right? This is my acid, again, acid base adduct. But this is still simply just a Lewis base. I know it's a Lewis base because here, right, here's some bonding electrons. Here's some bonding electrons, right? So we would get silver. And this has a positive charge, or silver has a positive charge of +1. I have two that are negative, so my new acid-base adduct has a negative charge. So I now have a new acid-base adduct from that reaction. So when we look at these, is that we can promote the bonding of another base with these acid-base adducts, with these other complex ions. So when we're looking at these, right, um, the transition metals, right? So transition metals, don't worry about filling the octet rule for them, right? Don't worry about filling the octet rule for them. We only really want to fill the octet rule for these Lewis bases, right? So a Lewis base would need to have 8 electrons. So if I'm looking at NH3, right? Here's 2 electrons here, here's 2 electrons here, here's 2 electrons here, and I'm going to need another set of electrons to get me that octet rule, right? So if we look at hydroxide, right? Hydroxide, here's 2, 4, 6. Bonded to the hydrogen is another charge here, but we do have an overall charge of minus, where we have a negative charge here. So when we're looking at a case like this here, right? How do I know the carbon's going to bond and not the nitrogen? How do we know that that's going to bond? Well, this is where we go and we work on bond order, right? Is that when I look at this as being electronegative, um, is that we're gonna take a look at this. And I guess we just, man, this is just kind of second nature to me. But we did want to go and how much can bond to one another. So we don't want to make more than 4 bonds, right? We're not going to be making 5 bonds. The transition metals, um, as long as we're further down on the periodic table, beyond periods, beyond period 2, we can make more bonds. But the general rule here is we're not going to want to make more than 4 bonds with any of our polyatomics that we use, any of these Lewis bases that we're going to use. We're still going to want to stick to the 4 bond rule, right? That's not, we're not going to be making double bonds here, right? We're not going to be making, we're not going to be adding 5 bonds to carbon. We just kind of want to still stay with the general rule. We still want to stay with the general rule that we're just going to have 4 bonds to each one. As far as the positive and negative charges go, that's pretty much just some simple math. Like Brenda already calculated one of them. When we're looking at these, I know the overall charge here is plus simply because, well, this is 1 plus and this is neutral. So by putting those together, I come out with a positive charge. I have 1 plus here, but I have 2 negative charges here. I know that my overall charge is going to be negative, right? So those are overall charges. Oh my God, somebody's at the door again. Hold on 1 second. All right, resume recording. All right, so oh, before that goes away, okay, we can still see that again. The other thing that we have to decide here is that how do I know not to bond the nitrogen as as opposed to the carbon? How do I know that the carbon is going to bond to the silver? And this is when we look at formal charge, right? You guys remember formal charge? Formal charge, we take the group number minus the number of bonds minus the number of electrons. So here, if we take carbon's in group number 4, minus the number of bonds, minus the number of electrons, or how many lone pairs it has, uh, equals -5. Nitrogen is group number 5, minus the number of bonds, 3 bonds, minus 3, minus 2 electrons in the lone pairs. So here, formal charge of 0. Here, right? So my formal charge on the nitrogen is 0, but I have a negative charge on the carbon. So being that silver has a positive charge, well, is the nitrogen going to bond to the silver, or is the carbon going to bond to the silver, right? Is that we would have the negative charge on carbon attracted to that positive charge on the silver. And that's how I know whether to bond the carbon or the nitrogen, is by using the formal charge. Does that help out, Brenda?
Yes, thank you.
Okay. Yeah, no problem at all. Um, no, I'm not going to erase that. I'll leave that there. That's fine. All right. Let's take a look at about something else here. How about we take a look at zinc hydroxide? Not 4. I need an ion here. I'll put 4, and then this will be a 2 minus charge. So we're going to get some zinc, 2 plus I'm going to get 4 hydroxides. And again, because of transition metals, don't worry about um, the octet rule or the 4 bond rule for these transition elements. Okay, so now that we have these ions, is that we can actually um, use this common ion effect and apply it to these acid-base adducts, right? Is that if we enter another base in here, because this is now in solution, if I were to add a new base into that solution, is that would, see, we got 2 plus here, is that we can use that to get a new adduct here. And we're going to have some zinc H3. We should have excess though. This is, we're going to consider this saturated solution. Um, 2 plus. Aqueous. 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 So, erase, erase, erase. So when mixing these solutions together, by mixing a solution of zinc hydroxide and by mixing a solution of um, in a solution of ammonia, looking at both of these, reactions, I see this common ion here, and I'm going to write a third reaction. This is the net reaction here. From a combination of both of these reactions is I'm going to have a net reaction, and my net reaction is this zinc hydroxide plus some ammonia, and we're going to get this net reaction here from that. So by using this common ion effect, is that we can come up with these net reactions, and we can come up with these. If I use one particular adduct and I add another base to it, well, what's going to be the result of that? I'm going to have this new Lewis, or this new acid-base adduct, but I really want to see the whole reaction. I really want to know the entire reaction of pushing and moving this particular ligand here. So these are what we call, I should introduce that term now, is that these are what we call ligands, right? So we can go back up here. This is a ligand. This is a ligand, right? All of these polyatomics, all of these bases that we attach to these complex ions are what we consider ligands. And by taking these complex ions, by taking these acid-base adducts, is that we can change these ligands, right? We can change these ligands to come up with other acid-base adducts. Let's take a look. So here, and I should probably write something here. So something in particular. So let me write kind of a title for this one. This one is, we'll say this is the dissolution. Dissolution, about equation. Equation of dissolution of zinc hydroxide in ammonia. right? So this is our equation of dissolution of zinc hydroxide in a solution of ammonia, right? We took our zinc hydroxide and we wrote a reaction for its dissolution. And then if we take that and put it in a solution of ammonia, well, what's going to happen? Well, we're going to get this new complex ion here. Let's practice with that one more. So how about we'll do a dissolution of lead iodide in a solution of nitrate. In a solution of nitrate. So how are we going to dissolve this in a solution of nitrate? So if I put PbI2, I need this. This is going to be a solid actually. Is that I need that to dissolve, and the reaction for that becomes Pb2 plus 2, right? Here's my reaction for it dissolving. But now what's going to happen if I put this in a solution of nitrate? Well, is that this lead plus this nitrate is going to make lead nitrate aqueous. This is aqueous. This is aqueous. And so the equation, let me put that in here too. So our equation of dissolution for lead iodide, lead 2 iodide in a solution of nitrate is simply, let me combine these here together, right? I don't need to see both of these in the reaction here, is that if I take some lead iodide plus put that in a solution of nitrate, we're going to get plus, right? So here is my net equation for the dissolution of lead iodide in a solution of nitrate. Is that first we have to come up with the reaction on how we're going to split that up into aqueous ions, and then add those ions into a solution of nitrate, right? So these ligands here, right? So these, and let me draw this out for you guys. We'll do nitrate here. Minus, minus, plus, no charge on that. 2 plus, that's 2 minus. But here again, these are what we consider, ligands, right? Ligands can be neutral or ions, right? These ligands here, nitrate has a 1 minus charge, but as we saw earlier, we also used ammonia, and that was, we bonded that to silver, and those were neutral. So ligands can be neutral or they can be charged, right? I'll put some examples here, like water can be a ligand, ammonia can be a ligand. Those are both neutral. We can put, we saw cyanide. We've used hydroxide, we've used nitrate. So these aren't the only ligands here, but these are just so you know that ligands could either be neutral or they can be ionic. Um, let's use the same equation here. So let's use Pb2 plus aqueous plus 2 nitrates, and we got PbNO3 2 aqueous. All right, so we're going to do another K value here. So there's another K value here. We took these two ions and we formed this aqueous solution here of lead 2 nitrate. So the new K value here is we're going to have what we call a formation constant. And this is going to be K sub F. So K sub F. So if we look at this reaction here, well, using our law of mass action, we always do, right, products over reactants, that Kf is equal to Pb, let me rewrite that, over our reactants, because this is all aqueous, I don't have any solids here. Is that here we have what's called our Kf. And this is actually equal to, because we also need to, if we have a formation constant, we're also going to have a dissociation constant. And it is just simply the inverse value. So this is actually equal to 1 over the dissociation constant, right? So our dissociation constant, so our K sub D is going to equal, right, our dissociation constant. That would be me flipping this around. That would mean that I would have my PbNO3 as my reactant, and my products would be Pb2 plus and 2NO3 if I'm dissociating this. All right, so there we have our Kf, or our formation constant, and Kd here, and this is equal. The relationship between the formation constant and the dissociation constant is an inverse value, right? So our Kf is equal to 1 over Kd, and our Kd is equal to 1 over Kf, looking at these different values that we have here. Oh, let's see, can we get it? I'd like to do a calculation involving this. Um, so let's look at a reaction. How about we take, um, we're going to add some aqueous cyanide. We're going to add some aqueous cyanide to some zinc sulfide. All right, so let's work with this one first. We're going to take this here. So this, we have some zinc sulfide solid. And we need to break that up into some aqueous solution, and we're going to have some zinc ions, plus we'll have some sulfide ions. But now we need to introduce that. So we're taking the zinc sulfide and we're going to introduce it and put it into a solution of cyanide, which means that our zinc ions are going to react with that cyanide. Actually, we're going to have when we do this, and don't worry about this. For these types of reactions, um, I will provide you the saturated solution. Right? Is that here we when we talk about these, is that we always talk about what we call a saturated solution in order to do this. So I'm not going to add. I'm going to add 4 moles of cyanide, and I wouldn't expect you guys to do that portion there. Is that um, on on the exam is that I would provide you with this information, right? I would provide you with part of the reaction, right? But then I would expect you, if I were to provide you this, I would expect that you guys would know how to put that together. And you would say, okay, that I have some zinc. And what's the charge on this going to be? Well, I know the charge on this is going to be 2 minus, and it is aqueous, right? That I would expect you to know. So don't worry about where you're going to get this information from, is that I'll provide you that, but you need to determine what the product is going to be from that. All right. So now let's do our KF. So our KF is equal to over so here's that. And do we know the formation constant of it? Let's see. So the formation constant is, I believe, in Appendix K. There's Appendix J, and we should see K sub F somewhere in here. Solubility. There they are. So Appendix K, we'll see our formation complexes. So let's see if we can find zinc cyanide here. There it is. Perfect. Right? Zinc cyanide is 2.1 times 10 to the 19. And that is the formation constant. So we'll write that off to the side. We're going to say Kf is equal to 2.1 times 10 to the 19. All right, 2.1 times 10 to the 19. Well, my question here is, can calculate KD. Well, can you calculate KD from this? Sure, absolutely, because our relationship KF is equal to 1 over KD, right? Calculation is equal to 1 over KD. So let's see what our KD actually is. So KD, our KD would be flip the other way around, where we're going to have zinc 2 plus fourth here. And this is equal to 1 over KF. So my KD is equal to 1 over 2.1 times 10 to the 19. 2.1 times 10 to the 19. 4.76 times 10 to the minus 20. Sorry, KD is 4.76 times 10 to the minus 20. All right. Let's see here. But we do some more calculations here. So let's calculate Let's calculate some equilibrium concentrations. Let's calculate some equilibrium concentration. Let me give you a KD here. So our KD is equal to 7.8 times 10 to the minus 18. And I'm going to have you calculate the concentration of cadmium and the concentration of cyanide in a 0.250 molar solution of cadmium cyanide for... All right. So our KD here. So let's put this together. So let's do um, calculate the concentrations. I'm given the KD, so we'll do... All right, so here's my reaction. Because I'm given the KD here, not the KF. So uh, I do have my KD here. Let's take a look at this. Ice table for this. They're all aqueous. This is aqueous. This is also aqueous. So um, just as a note is that our ions are never solid, right? We don't have solid ions. That kind of violates electro uh, negativity rules. Um, by having a charged solid. All of our solids are neutral. And they're not going to have a charge on it. So if we see something with an ion like this, we're assuming that that's aqueous, and that it's not going to be a solid. So initially here, I don't have any of this. I don't have any of this, but I do have 0.250. Oh, I don't need the M there. 0.250 here. So it's going to be plus x minus x 0.250 minus x. All right. So our KD in this point, and calculate equilibrium concentrations. We don't have, let me see here. I need to double check here. That we're not given dissociation constants in another. Okay, so we don't, okay, so we're not given any dissociation constants. Is that we're only given formation constants, right? So because I have the KD, and we need the KF, is the reason why that it's written this way. So if anybody's wondering why, I wrote it this particular way, because in the previous one here, right, I'm given the KF, right? So I'm gonna write it this particular way, right? Here, I need to figure out what the KF is. I don't know what it is. So this is why we write it this particular way, right? Because I'm given the KD in this part here, and here I'm given the KF, right? So those are written different ways, right? So here, our KF is going to be, uh, let me see, what is our KD value? Because this constant, right, our K value is a lot less than 1, I'm going to make an assumption here. And let's see, our Kf is equal to 0.250 over, this is 4x. Oh man, that's going to make some mistakes here. This is 4x. So we're going to have x times 4x to the fourth. So x times 4x to the fourth, which means that our KD is equal to the inverse of that. Our KD is actually equal to x times 4x to the fourth over 0.250, right? And this is equal to 7.8 times 10 to the minus 18. That's a bad 8, right? So here 10 to the minus 8 because that's the value we were given there. So if we calculate this, what do we have here? We have 4 to the fourth, 4 times 4 times 4 times 4, 256 x to the fifth over 0.250 is equal to 7.8 times 10 to the minus 18. If we do some math here, let's get x by itself. X is equal 7.8 times 10 to the 18 minus 18 times 250 divided by 256 is equal to 7.62 times 10 to the minus 21. All right, so how do we figure out what x is? Well, we take the fifth root of that. If you don't have a fancy calculator, that's okay. So you can either do this, 7.62 times 10 to the negative 21, or you can write it as 7.62 times 10 to the minus 21 to the 1/5. So let's see what our x value is. So x is then equal to 9.5 times 10 to the minus 5. And now that we know what x is, right? We know what x is. We can figure out these concentrations here. X is simply, so concentration of cadmium. This solution is going to be 9.5 times 10 to the minus 5. And let's see this calculation here. We're going to go, was it cyanide? Was that it? Cyanide, yeah. Equals 4 times that amount. 4 times 9.5 times 10 to the minus 5. And whatever value that comes out to be, 38 or something. 3.8 times 10 to the minus 4, something like that. 3.8, something like that, right? So we can figure out those concentrations there. Let's do another one. Calculate some more concentrations, more ice tables, more concentrations. How about this? Nope, let me write it in blue. Let's calculate concentration of copper. Concentration of copper in a 0.050 molar solution of, how about some copper? This is going to be 2 plus. All right. So let's go with the KF. Let me give you the KFs. So if we're given the KF here, KF 1.7 times 10 to the minus 13. That's copper. Let me make sure that's the right one. 1.7 times 10 to the 13. Is that what I have? Yep, 1.7 times 10 to the 13. So because we're given the KF now, right, we're writing it this way. So I have copper here. So this is my formation constant provided. So we are going to write it different. Aqueous. We're going to get some copper 2 plus. Aqueous plus we're going to get 4 ammonia, also aqueous. So here, the KD, right? KD is opposite of the KF, right? Oh, let me clean that up. So our KD is going to be, oh, KD is written here. So we're going to say this is copper 2 plus. H3 fourth. And yep, there we go. So there is our KD. And our KF would be the inverse of that, right? So here, what do we have here? KF. Sorry, might cut out there. KF is going to be the inverse of that, so we're going to go CU. All right, so we have our KF here. Let's do an ice table now. I should have wrote the ice table earlier, but I didn't. Ice table here, we have a concentration of 0.050. This is going to be 0. This is going to be 0. Minus x plus x plus 4x. 0.050 minus x, x, 4x. So if we use the formation constant here, this is what we're looking at. Is that, let's see, KF is equal to 1.7 times 10 to the minus 13. Or was it 13 or minus 13? Oh, I have the wrong. It is positive 13. There we go. This is going to equal our products over reactants. So looking at our ice table here, I'm going to make an assumption because this is so much larger, right? If it's a lot less than 1, if it's a lot more than 1, I could still make the assumption here because our K is greater, much greater than 1. I'm just going to put 0.050 over x times 4x to the fourth. So let's go ahead and clean that up a bit. So we're going to have 1.7 times 10 to the 13 is equal to 0.050 over 256 x to the fifth. All right, so now we need to clean this up a little bit more here. Let's clean this up. How do we clean this up? So we'll go 256 x to the fifth is equal to 0.050 over 1.7 times 10 to the 13. And then we can say x to the fifth is equal to 0.050 over 1.7 times 10 to the 13, 6. And let's see what x is. X is equal to, I don't think I'm going to write this one. I've shown you guys a couple times already. So I'm just going to solve for x here. And our x is equal to 4.1 times 10 to the minus 5. So either way, if you take the fifth root of that, or if you do it to the power of 1 over 5, you'll get the same answer. But we now know what our x value is. So concentration of copper is going to equal 4.1 times 10 to the minus 5. Copper of ammonia would simply just be equal to 4 times 4.1 times 10 to the minus 5. Um, you know what? And to be honest with you, if you guys left this as an answer, I would accept it. Like, that's perfectly fine. I can put that in the calculator and calculate that out. That's not a big deal. But you know, if this was an exam and you guys had put that as an answer, that's perfectly acceptable. 4 times 4.1 times 10 to the negative 5. But I think this will, yeah, we went a little bit over, but we did finish this section of chapter 13. Um, yeah, so I think we are still on track here. For those of you that haven't seen it, let me stop the video here. Stop the